Good afternoon, dear students. There appears to be $28 students thus far. Okay, which is good. Now, at my end, there's heavy rain going on in this place, so perhaps it may affect the recording and the sound. So let's start today's session. So we are doing CCNA-1, Introduction to Networks. Okay. And we are doing Module 8, the network layer. If you remember the OSI model, the first layer, we have the physical layer. Then we have the data link. Above that, we have got the network layer. Okay. So the third layer is what we are going to study today. On the surface, what information you have is that data link layer is mainly responsible for your MAC addresses. But when you go to the network layer, then you're talking about the IP addresses, IP version 4, IP version 6, which are the logical addresses. Okay. So keeping that in mind, let's dive into network layer and learn more about it. Okay, Cassandra. Okay. I'm using one of those mics, you know, the professional expensive ones. You know what it does? It cancels the distant objects, distant sounds. Okay. And that's why my mouth is just on top of it. If I go back, you see, as I'm going back, uh, the sound quality may not be that good. Okay. Thanks, Cassandra. Anyway, let's start. So what we're going to study today is look at some of the characteristics of network layer. Okay. What protocols they use for reliable communications. Look at IP version 4 packet, IP version 6 packet. What are the different header fields of these packets? How does a device route? Okay, how does how network devices use their routing tables to direct packets to a destination network? Okay, this morning, during the morning session, we discussed that there is a table inside a switch which has information about all the devices connected to the network. That table will mention what is the device and what is its uh, MAC address. Okay, so that next time it has to find that same device, it can quickly know where it is and it is on which port. Similarly, your router has got a table, okay, with information about which is the next route it has to take, which is the next hop it has to take, and so on. And then routing tables, okay, router routing tables. So explain the function of fields in the routing table of a router. So these are some of the things we're gonna go through today. First of all, some characteristics of the network layer. Okay, the network layer being the third layer in the OSI model. In the OSI model, if you look over here, at the bottom we have got our physical layer, goes up to the data link layer, goes up to the network layer, then goes to the transport layer, session, presentation, and application we usually identify them just as application layer. Okay, please forgive my mouse handwriting. Okay, so we usually identify them as application layer. So sending from a source to a destination, what is the source IP address, the logical address? What is the destination IP address, the logical address? Okay, remember, we are not interested, we are in network layer. MAC address was in data link layer. Now we are only concentrating, we are looking at network layers and the logical address. The source, the destination, you can see right on the surface. When you see this, you can see they are on different networks. Okay, that means it has to travel through a router. Okay, it has to travel through a router to send the data from here to here. Okay, there, it has to travel through a router or a series of routers. So that's what we are interested to know. How end devices, okay, end devices like your computers, your mobile devices, your IoT devices, these are end devices. Switches and routers are intermediary devices. Okay, so network layer is responsible for end devices exchanging data. And the principal protocols that it uses to ensure communication happens is IP version 4, as you can see over here, and IP version 6. Okay. So network layer, we can say on the it has got 4 main functions. Number 1, addressing end devices. What kind of address? Logical address. Encapsulation. Encapsulation of what? Encapsulation of the segment that is created in the transport layer. Remember, your data comes from the application layer, segmented in the transport layer. Okay, so that segment has to be encapsulated inside your network layer. And then from the packets will be sent down to your data link layer, and then broken into chunks of frames, and these frames will be sent to the physical layer as bits and bytes. Okay. Network layer is also responsible for routing. Okay. I told you, every router, just like this morning, we discussed, every switch has got a table. In that table, it has information about all the devices connected to it. What is the MAC address? And they are on which port? Every time, every 5 minutes, it updates that information. And every time you update, you connect a new device or you take the old device and make some changes, it keeps updating. Okay, that's why it's dynamic. Your router also has got a table, a routing table, so that when a message comes from the source, it can immediately know which router it has to go to. Should it go to this one? Should it go to this one? Okay. And as part of what we are doing over here is studying how we can configure the router. You can configure it statically by doing static routing. You can configure that whenever something comes, I want you to send it through this router. This would be the second hop. Or it can be dynamic. Okay, all these things you will configure. And this is something that you study in CCNA-2. Okay. If you are encapsulating the segment when you are sending it, when you're receiving it, okay, when you're coming in this way, okay, you're also de-encapsulating the segment. So you give the segment to the transport layer. And then transport layer takes that segment and decodes it back to data. And the data is passed to the application layer to read and make sense of it. Okay, so these are the 4 functions that we have of our network layer. Encapsulation, as we said, when you come from the transport layer, the segment, okay, is encapsulated into a PDU. And that is one of the functions of your network layer. Doesn't matter what logical address you're using, can be IP version 4 or IP version 6. All the packets, network layer is responsible to take it from the source to the destination. And that source and destination address, be it IP version 4 or IP version 6, does not change. It's the same. So we have something actually called NAT, Network Address Translation, okay, which is responsible for enhancing IP version 4. You see, IP version 4 had a problem, and that problem was we couldn't have enough IP version 4 addresses, especially public addresses, because they are being they are not enough. And you know, how many people are there in the world at the present? 7 billion, 8 billion. Now 7 billion, 8 billion. Just imagine of how many devices do we have? Even 3 billion devices. And if 3 billion, if each person, say 3 billion people, each has one device, and we know that each of us don't use just one device with the NIC. We have got so many devices. Okay, I just look around my table and I'm surrounded by so many devices, and you do the same. You will see that you're surrounded by so many devices. So just sticking with IP version 4 doesn't satisfy our need. We have to go to IP version 6. But before we went to IP version 6, we had an intermediary solution, and that solution was NAT. Okay, so what NAT, in a long story short, what we did was we took all the Ethernet local area network IP version 4 address and mapped it to one public IP version 4 address, and that public one was your NAT. Okay, so NAT means taking your individual local area network IP version 4 address and mapping it to one public address. But now we don't have to use that because we have got IP version 6. IP version 6 has been created to solve our problem. NAT was a temporary solution. Having said that, you can still implement it, but it doesn't make sense much now because we have got IP version 6. Talking about IP, remember when you studied in your lecture, in the first lecture itself, you studied that there are 2 ways of communication. And one was, first you build a circuit, like how you do a phone call. You pick the phone, you dial the number, dedicated circuit is established, and then you talk. That is one way, okay? And then there is the internet way, the datagram way, the IP way. No need to establish the circuit. Send the data. Don't care about it. Just send the data. Okay? So that is the whole idea of, remember in the early days of internet, when World Wide Web was known as World Wide Wait, in those days, they didn't care about, first establish a connection and then, no, just send the data. No need for acknowledgement. No need to check for, whether the The receiver has got the destination has received it. There are other protocols that take care of that. Okay, so that's what IP is uh, here for. The main reason we have IP is to reduce any kind of overhead, make things simpler by making it connectionless, best effort, and media independent. We don't care. It can be uh, high bandwidth copper wires, it can be fiber optic, or what we had in the 80s and 90s, it can be our telephone cables. Okay. So IP has been designed, okay, to be connectionless. That means it doesn't establish a dedicated connection with the destination. No circuit. Okay. Now, again, you have studied this in your lecture. For example, we have got asynchronous transfer mode, ATM. Okay. That one is first establishing a dedicated circuit, but ATM is again obsolete. We don't use it. Okay. In fact, most of the things that we had now, because of the backbone that we are building, fiber optic backbone, you can see that uh, most of the communication is faster. Okay, how do you think we stream? We couldn't have streamed in the 80s or the 90s. It was not possible because that kind of connection cannot, support that. But now we can because we have got this uh, fiber optic backbone. Okay. So if I go to fiber optic submarine cable network, just go to the images and you can have an idea. I think I've shown you this. You see, undersea, we have got these fiber optic cables all around the world. There's so many maps, my dear students. Okay. And you can actually go on one. Mm. We can have a look and you can see so much activity around our area. Okay. And this is, still building up. Okay, these undersea cables. So anyway, let's not go to other stuff. What I'm trying to tell you is that in IP, in the initial days, and even now, there's no control information needed, no synchronization, no need to get an acknowledgement, okay? No two-army problem. Two-army problem is something that you haven't studied yet. You will study in your lecture. The destination will receive the packet when it arrives, but no pre-notification are sent by the IP. Okay, no pre-notification. So no need for connection-oriented traffic. Rather, best effort. Again, something that you have studied in your lecture. It will concentrate on best effort. Yes, IP is best effort. Okay? There's no guarantee. There are other protocols which will take care of data being arrived at the destination or no. This reduces overhead and makes IP the most convenient protocol for internet. Okay. No acknowledgement. So it reduces overhead. And it even doesn't know whether the other device is received the packet or not. And then you ask yourself the question, hey, then how do you know? How do we ensure that the data is traveling? Okay. Uh, so those things actually, it relies on other protocols for ensuring that the destination has got the data. Okay. And it doesn't even retransmit after an error. Okay. It cannot put the sequence of the packets in order. No, it doesn't do that. So that is why we call it best effort. And this is a technology that survived. Okay. Your IP has survived right from the 80s. 90s, we introduced the World Wide Web. Tim Berners-Lee created a new technology. Okay, his main goal was to share research papers. He was working at CERN, and his main goal was to share research paper. Easier way to search research paper. Very simple. I create an HTML page. You use a protocol known as HTTP. Get the HTML page from my computer, which is a server, to your computer, which is a client. That's it. World Wide Web was born. Okay. The politicians, mainly Al Gore in US, took that idea and technology and implemented it and created your internet, the internet that we know. And then businesses took interest, and then people realized that, hey, you can do trade on this. Okay. And that's how your World Wide Web came out of this IP. IP is also media independent. It doesn't care how do you transmit your data. Are you using copper serial? Are you using optical fiber? Are you using wireless? It doesn't care. Okay. As it says, best effort, send. Other protocols will check and find out whether the data has been received. If not received, then perhaps it will send again. Okay. Every time you want to send the data, network layer does something. Okay. Did I miss anything over here? No. Yeah. Network layer does something. What it does is it establishes the maximum transmission unit, that is known as MTU. Okay. So once it establishes the MTU, okay, then it can perhaps send the data. So what does the network layer do? It splits the packet into small fragments. Okay. Yes, fragmentation sometimes delays the transmission of data. Okay. So that is something that you don't see in IP version 6. It doesn't do fragmentation. But in IP version 4, yes, you do fragmentation. And then these fragments are converted into electronic signals in form of bits and sent to the destination. And at the destination, the reverse process happens. These bits and signals are taken and configured into fragments into packets to segments to data. Okay. Now, let's go and have a look at IP version 4 packet and IP version 6 packet. Okay, get an idea. IP version 4 is being replaced with IP version 6. That is true. For public addresses, my dear students. Now, students, you shouldn't think that, whoa, no more IP version 4. Okay, this was a technology that we had since the 60s, and now it has lived its life and it's going to go away. No, not yet, not so soon. We know that IP version 6 is going to be here for another more than 100 years. How do we know that? I'll show you in a while. But IP version 4 is not going away. That is why even when you study CCNA-1, they still teach you, they concentrate on IP version 4. Why? Anyone can tell me why? Why do you think IP version 4 is still important? Yes, you cannot use IP version 4 for public addressing. You cannot put it on a computer and put it on the internet because it doesn't have enough addresses. But it is still important. Why? Anyone? Yes. Who is this? Yes, LoGN, you're right. Because our Ethernet, our local area network technology, still you can use IP version 4. Very good. Okay. So That is why we have to learn this technology, okay? So the IP version 4 being the primary communication protocol for the network layer, the header has got some purposes. First of all, send it in the correct direction. Have the information about different fields in the header, and use this information in all parts of the network that handle the packet. Every device, every intermediary device, be it switch, be it router, will look at the header and know where this packet has come from and where is it going. Okay? So this is what it looks like. Okay? It has got several fields of information. Okay? The two most important fields are source and destination, IP address. Okay, so let's look at some of the function of these fields in detail. If you look, you have got a version right here. So the version will be version 4 because it's IP version 4 header. So next you have got your differentiated services. It will tell what kind of service it is doing. Okay. You'll have a checksum. The checksum will check whether the header, there is a corruption, there is a data corruption or any kind of corruption in the header. And then you also have a TTL. The TTL will be the time to live. So giving a time to live, it will say that, okay, I want this header perhaps to carry its data for 3 hops. That means within 3 router count. Okay, so first router count, the 3 will become 2, then the 2 will become 1, then the 1 will become 0. Once it becomes 0, the router will discard the packet. Okay, depends on how many hops you have to take to reach your destination. Okay, for example, how many hops do you have to take to go from your computer to Google? Okay, there's a command you can find out actually. Okay, we're going to do all these things. It will tell you. And you know, it's not always the same because there are different routes. There's so many redundant routes, and one may go down, the other will take its place. Okay. It always finds the, if you're using, for example, uh, different kinds of technology, for example, if you're using OSPF, it will always find the shortest path. Okay. Protocol, it will tell you what kind of protocol you're going to use. And of course, the source IP address, where is it coming from, and the destination IP address. This is your version 4, IP version 4 header. This is what it looks like. Now let's have a look at the same thing with IP version 6. Okay. The problem with IP version 4, as we said, public addresses run out. Okay. Lack of end-to-end connectivity. That is why we created NAT, a temporary solution. Okay. What we do is map the private address to a public NAT address. Okay. The problem with that is NAT is very complex to implement, and has got troubleshooting issues. That is why we had created, not we, IETF, Internet Engineering Task Force. They did an amazing job and created IP version 6 addressing system. Okay. So IP version 4 consisted of 32 bits. IP version 6 has 128 bits. Okay, isn't that amazing? Okay. So that is 96 bits more then 32. Just looking at it, you see, get an idea of what I'm talking about. You see, there are 4 billion IP version 4 addresses. So if you want to go public, let's talk about, I'm not talking about the address that you give in your network, okay? That one nobody cares because it's in your network. As long as you don't duplicate in your network, in your Ethernet, no problem. But that is within the Ethernet. That means you only use switches to connect. Switches and aggregate switches and all that. But the moment you take that IP version 4 address and make it public, it may clash with another computer that has the same address. That is the issue that we have. 4 billion is not enough. I just gave you we have got more devices, and IoT is another thing that every day we have got new devices coming in. Every day, people are coming out with new technology, and every time a new technology means an IoT device connected to your network. Even when you go and buy a decent, not a simple camera, it comes with an NIC where you have to automatically give a logical address. Okay, so anything that has got this network connection, it needs a logical address. So IP version 4 doesn't do the job. 4 billion only. Now, let's look at these numbers. When you look at million, we have got 6 zeros. Billion, 9 zeros. Trillion, 12 zeros. So for IP version 6, you have got 340 undecillion IP version 6 addresses. So to put that scale in perspective, 1 undecillion is 10 to the power of 36 zeros. That means 36 zeros. Now we are talking about 340 of those. So given the scale of the improvements and technological advances that we are going through at this stage, adding new devices, we will run out of IP version 6 address in more than 100 years. So maybe after that, we have to come out with a new technology. You get an idea? Okay. And we're talking about public addresses, you know. That's it. Add your device, put it on the internet. Okay. And give it an IP version 6 address. Okay. So we are talking about public addresses. So this is the benefit of using your IP version 6 address. It has got other benefits, like it has got improved packet handling, okay, because it's got fewer fields, and there's no need to do NAT, which is complicated. So let's have a look at IP version 6 packet, okay. It is simplified. We cannot say it's smaller, but simplified. Header is fixed as 40 bytes, okay, and some of the redundant fields were removed. Okay, like there's no flag, there's no fragment offset, and there's no header checksum. So these are the different fields that you have in IP version 6. Let's have a better look at it. You have got a version, again, which says it is version 6 or version 4. A flow label. This informs the device to handle identical flow labels the same way. Okay. From the destination to the source, the same flow label. Payload length, okay, will tell you what is the size or the payload of your IP version 6 packet. Next header ID is the next level protocol that you're going to use. Hop limit, it replaces your time to live that you have in IP version 4. Okay, so here again, if you say 3 hops, that means after 3 routers, no more going to another router. And finally, the source IP version 6 address and the destination IP version 6 address. Okay. Sometimes your IP version 6 packet may have extension headers. Okay, these provide optional network layer information. Optional being the key word, not necessary, but if you want, your network can have that information. Okay. And as we discussed, IP version 6 does not fragment the packets. Okay. So that is perhaps another added benefit, because fragmentation, as we studied, creates latency. So if you're using IP version 6, you're removing that latency. Okay. Now, how a host routes. Let's go into details of this and understand. Within a network, we already studied this morning that you send your data to a table in the switch. The switch looks at the MAC address and registers it if it's not in the table. If it's in the table, it takes your data and immediately sends it to the destination because it has the MAC address and the port from where it has to go and reach that destination MAC. Now let's study if you go outside the network, how it does that. So from the source, when you create a packet, okay, how does it leave the network? Okay. First of all, you should know you can send a packet, to yourself. If you're using IP version 4, you want to check your IP TCP IP connection, you can do a self check. You can send a packet to yourself. And IP version 4, it is 127.0.0.0.1. This means, okay, your local host. And you can do the same thing in IP version 6:::1. You see the benefit of, instead of typing this, I just type this. You can see the benefit of IP version 6. Makes things so much simpler. We can try it out. Okay, let's just, on my PC, I go to my command prompt. Okay, and there it is. I've got a big microphone in front of me, so typing is not so easy. So be patient with me, my dear students. So I type ping 127.0.0.1. That means IP version 4 localhost. There. Reply, reply, reply. Okay? So everything is okay. I can do the same thing, but instead of IP version 4, I say I want IP version 6. Okay? 1. There. Reply, reply, reply. Okay? I can also just type ping localhost. Okay, reply, reply, reply. Localhost, that means you're talking about your IP version 6. The command would be : 1. Okay, so my PC, the TCP IP, everything is perfect. It's working. Okay, that's how you check. So a host, a device, can send packets to yourself, to the other host, okay, as long as you're in the same LAN. Now, same LAN means before you come to the router. This connection is known as gateway. Okay? So this gateway will have the same IP address as the network. Look at this network. What is this network? This network is, what is the network address? 192.168.10.0/24. /24 means 255.255.255.0. In other words, it means this network consists of 8 plus 8 plus 8. 24 bits for the network, 8 bits for the host. Okay, that means 192.168.10 will always be the same. The only change that you have to do is in the host portion. So the router gateway, we give 192.168.10.1. This host, we give 192.168.10.15. This host, we give 192.168.10.10. Okay. Question: how many devices you can add to this network? We calculate. Okay, we calculate over here. How many host bits we have? 8. 2 to the power of 8 minus 2. Okay, what is the result? Anyone? Can you please tell me 2 to the power of 8 minus 2 is how much? Waiting. Cassandra? Is it right? Host is 8 bits, correct? Yes. Well done. Again, GN 254. Okay. So over here, what we do, we are saying that we can have 254 devices in this network. Okay. But we are giving addresses only to 3 devices, but the potential devices are 254. Now, the last address 255 is reserved for what? That means 192, please forgive my mouse handwriting, dot 168 dot 10 dot 255. What is it reserved for? Yes, well done, Cassandra. This is your broadcast address. That's why you cannot use this. That means if the source gives this IP address, if 19, this 9 looks like 1, sorry. If 192.168.10.10 gives this destination address, this one will get it, this one will also get it. Okay, but it will not go outside the router. That's why routers are called broadcast killers. Okay, broadcast is only within the IP version 4 network. Okay, so having that in mind, okay, these are the local hosts. Now, the moment you want to go and access this computer, the remote host, you have to go through a router. Okay, these are devices that are not on the same LAN. Okay, that is why we need a router. Now, router is something that we have not yet touched in the lab. We have not done any exercise on the router in the lab yet. But I have told you since the beginning the difference between a router and a switch. A switch is for the same network. When I say same network, you should ask, what do you mean by that? I mean, the network address of every device is the same. The moment the network address is different, okay, here's another network address, here's another network address, then you need a special machine known as a router. Okay. And these routers are the backbones of our internet. So the source device will determine whether the destination is local or remote. If it is local, okay, if it is local, it will send it, for example, if you are sending from this source .10 to 192.168.10.15, it will know that it's local. Just send it to 15. Okay? Like what we studied this morning. It will send it to the switch. Inside the switch, there is a MAC table. In the MAC table, it will find the MAC address of this PC2, and it will see which port it is coming from and immediately send it. Done. The problem is when you're sending to a remote host, then this PC 192.168.10.10 will only care about sending it to the gateway. Okay? It knows that it's not in the local. Okay? So the moment it goes inside this switch, it looks at the MAC table, it will see, hey, there's no such device. That means whenever you don't find a device in the local, just send it to the 192.168.10.1. Let this take care of it. Okay, that's not our problem. So everything which is remote goes to this router. So every IP version 4 uses its own IP address and subnet mask with the destination IP address. Okay, so subnet mask, I told you there are two ways. You can either use subnet mask like this. So /24 means 24 bits network. /24 means 255.255.255.0. Okay. You can either represent it in this way, or you can just mention 255. In IP version 6, the source uses the network address and prefix advertised by the local router, whatever the router says. Local traffic, the switch will take care of it, the local intermediary device. Remote traffic, the default gateway will take care of it. Usually, the default gateway will always have the address starting from 1. Okay? The default address will always start with 1. Usually, the first IP address we give to the router, the default gateway. Okay? That is why when you have devices, okay, in your network, when you have devices on your network, let's say we have a PC, okay, and we want to give a IP address to our PC, okay, you see over here it says, what is your gateway? Okay. So let's say I have a PC which is connected usually to a switch. Okay, let's connect it to the switch. Okay, there. Scared me for a while. And then the switch will be connected to the router. Okay, generally. You can connect the PC to a router straight also, if you want. Okay. So, whatever IP address you give to this connection, okay, you see I connected it to my gigabit Ethernet 00, okay? So whatever IP address I give to this connection, that will be the IP address of my default gateway. Okay. Now, in enterprise networks, usually we don't give static IP addresses. We select this DHCP because we have got so many devices. Every enterprise may have thousands of computers, wireless machines, wireless printers, connected printers, IoT devices. Okay, think about our university itself. So many devices. If you have the IT personnel have to go and give static IP address to every device, they'll go crazy. So what they do is they select this option, DHCP. When you have a DHCP, you have a computer or you have your router act as a DHCP server and automatically allocate IP addresses. Add a device, you will get a IP address automatically. Version 4 or version 6, a DHCP server can take care of that. Again, this is something you're going to study in CCNA-2. I'm just telling you for for your interest. So right now, let's talk about our forwarding, our routing. So if it is in the local network, it will send it to the local. The moment it sees that the destination is remote, it won't even care about finding. It will just know remote means send it to the gateway. This one will take care of it. Okay? So this one, okay, is our default gateway. The connection to this network would be our default gateway, and it will have the same IP address as this network. Okay, that means this IP address should be 192.168.10. The network address should be the same. The only change will be the host. Okay, so usually the gateway we give 1. Okay, that's a practice that we do, but it's not a must. You can change if you want. Okay. Okay. If your data is destined for a remote host, it has to go through the gateway. In the gateway, there is a table with information about other connections. And then from there, it is the problem of this R1. Whether it sends it to another router or whether it sends it to the network connected to it, we don't have to worry about it. As far as layer 3 is concerned, remember, your header has got information of the source and the destination. So that will never change. That will always be there. So the router knows, every router knows where it is coming from and where it has to go. Okay. Every host will know the default gateway, okay, which is this. Now, this default gateway, you either give it statically, okay? You either type it out, what is the default gateway, which we are going to do in CCNA2, okay? Give a static default gateway. Sorry, not in CCNA2, in CCNA1, we're going to do that, okay? Very soon, we're going to have router labs, okay? I think your lab 10 would be a router lab. A very important lab, something that perhaps will be implemented also in your skill-based exam, okay? Or we select DHCP. That means look for a DHCP server. A DHCP server is usually a router itself, which is configured to give IP addresses to the network, okay? IP version 6 sends the default gateway through a router solicitation, okay? So that means IP version 6 will try to find out what is your router. It will find which is the nearest router. Okay. So this one is actually the last route, okay, that it will find within the network. And if it wants to go to a remote network, it has to go through your DGW, your default gateway. You can actually find out in Windows itself what is the route to your default gateway. For example, all of you connected to the internet. You have to be, if you're listening to this class, if we are having this session, you're all connected to the internet. Okay. So what I can do is, you see, I can type CLS netstat. Okay. Over here, yeah, /R. Now, I'm connected to my gateway, which is my ISP is 192.168.0.1. My interface, my IP address, which is automatically given by this gateway, is 192.168.0.188. Okay. So there are 187 other devices, okay, within this network. Okay. So that means there is another computer with IP address 192.168.0.1. Okay. So actually you can do damage or play around, you know. You can do stuff like, you know, have you tried this command? Net send? You can do uh, play around, you know, you can go and find out. That is if your net send command has been enabled. Most probably they have disabled it. Okay. You can send messages with other people within the same network. Okay. So my router connection, okay, my gateway is this IP address. Okay. Now you find out what is your gateway. You can do that with your netstat. Okay. Okay, let's move on. Let's not linger. So it gives you information, okay, about all the interfaces, all the potential all the potential interfaces and MAC addresses. It shows you your IP version 4 routing table and IP version 6 routing table. Okay. So over here, I can see all those details actually are shown to me. Okay. Network destination, interfaces. Sorry. Okay. All those details are shown to me. So this is my IP version 4 root table, and it shows me my IP version 6 root table as well. Okay. So my IP version 6 gateway is this, as you can see. Okay. So my gateway has got both IP version 6 as well as IP version 4. Okay. Amazing things you can do, my dear students. You are just at the tip of the iceberg. The more you explore it, you can see that the iceberg uh, is on the tip of a big mountain, and it's the more you explore, you can see that you have got power on your fingers. You can use that power to do something great and also to do huge damage if you want. Okay, it's amazing what you're studying here. So let's look at routing. So every router over here has got a routing table. Okay. For example, here they're showing you R1's routing table. So this is R1, an example routing table. Now look at this routing table that we have. First of all, let's look at this architecture, this topology. We have got a network address, which is /24. That means network portion is here. This is the network portion. This is the host portion. Okay, again, host portion is 8 bits. That means 254 devices. I can see only 2 devices in this network, 2 IP addresses. Okay, the gateway is 1 and the PC is 10. Now there's another network between R1 and R2. What is the network address? It is 209.165.200.224. Okay, /30. See, not /24, /30. So when you say /30, what does it mean? How do you divide it? You're stuck, aren't you? Okay, don't be stuck. This means 30 is for network portion. And 32 minus 30, that means 2 is for the host portion. Okay, how do you divide this? Okay, this one is very straightforward. The 3 octets for the network, the last octet for the host. What about this? Very simple. /30 means, remember, /30 means 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is the first octet. 1, 2, 3, 4, 5, 6, 7, 8. The second octet. So remember, whenever you see ones, you're talking about network portion. Okay, 255.255 dot 1, 2, 3, 4, 5, 6, 7, 8. So that means the subnet mask, instead of writing /30, you can also write 255 dot 255 dot 255. Okay, you got 24 bits, but it's not 24, it's 30. Okay, so 24, 25, 26, 27, 28, 29, 30. The last 2 should be 0, 0. Okay, so geniuses, can one of you convert this binary to decimal? What is 111111100 in decimal? Can someone tell me? Use your calculator, quickly convert. 128 plus 64 plus 32 plus 16 plus 8 plus 4. What is it? 2, 5, 2. Okay? For those of us who are slow, just use your calculator. Okay? Okay. So what we do is 2, 5, 2. Binary is, there we go, 1, 1, 1, 1, correct. Okay. So here, this would be my subnet mask. You can represent it in this way, or you can just say \30. Okay. So that means 30 bits, all the ones are for network. Host bit is only 2 bits. So how many computers, or rather how many devices you can connect? 2 bits. That means 2 to the power of 2 minus 2 using the formula. That is equal to 4 minus 2. That means only 2 devices you can join in this network. And we are having only 2 devices. See? This and this. That is, you're connecting this gigabit Ethernet of router 1 to this gigabit Ethernet of router 2. Yes, GN, you're asking only 2 devices. Yes, only 2 devices, because you see, I'm using /30. I'm using this subnet mask. This subnet mask means only 2 devices. Okay, so my network address is 209.165.200.224. Remember, I cannot give this address. This is my network address. This is like 0. Remember, you cannot give this address. Similarly, you cannot give this address. Your first address is 209.165.200.225. Your second address is 209.165.200.226. Your third address is 209.165.200.227. 227 is what address? Can anyone tell me? Anyone? Those of you are still awake. Network address is 224. This interface is 225. This interface of R2 is 226. Then 227 will be what? Huh? No reaction? Yes, well done. GN and Mustafa, you're right. 227 is your broadcast address. Very good. Okay, so you're learning now. Okay, remember, after the last address, you add one, and that will be your broadcast. Okay, this is only for IP version 4. Okay, only for IP version 4, not IP version 6. Okay, IP version 4. So you get an idea. Now, if you want to send data from here to, let's say, your destination is 10.1.10. Now, I don't see that network over here because this network is 10.1.2. I don't know whether they made a mistake or they meant about some other network over here. Anyway, if you are sending from PC1 to this destination, PC1 will send the packet immediately to the gateway because it's not in a local network. The table, the MAC table, does not exist in the switch, in the local intermediary device. So it sends it to your gateway. Now the gateway will look at this IP address. Okay? And it will negotiate and see that, okay, since this packet, the best match for it is to send it to the next hop. So the next hop would be sending it to R2. Now R2 will see whether, of course, 10.1.1, okay, look at this network address is 10.1.1, okay, this one is 10.1.2. So definitely it's not this. Maybe they made a mistake in this diagram, but on the surface, you can see the network address doesn't match this. So R2 will perhaps send it to another router, another hop, okay, until it reaches its destination. Okay, so that's how, you see, the table, R1 table, okay. So the route that comes from from this network, okay. So the next hop is G000 interface, okay. If you want to go to this network, it is G001 interface. Okay, so if you're going through 10.1.0, then you have to travel through R2. Okay, so it doesn't care about where, it only knows that it has to send it to R2. And this is the technology of your internet. That's how communication happens. Routers communicating with each other and sending data to each other. Okay. Wait, there's a question. Good question, Cassandra. Remember that in every IP version 4 address, you should have a network address, and you should also have the first IP address, the last IP address, and you should also have a broadcast address. The broadcast address is the last network address plus 1. Okay. Even in a network, you see, in this network we calculated, there are only 2 bits for the host, only 2 bits for the host. So using the formula 2 to the power of 2 minus 2, that means you can have only 2 devices. Okay, only 2 devices. So the first device, the first IP address will be .225. You see, the network address, just add 1, 225. The second one will be 226. The third one will be 226 plus 227, which is your broadcast address. Yes. Every network will have, IP version 4 will have a broadcast address. It's a must. Okay? That means if I send over here a message or a packet by saying 209.165.200.227, it will send it also to R2, even if it is 1, because it's still broadcast. Okay? So whenever you look at IP version 4, remember, every IP address, you have to look at the network address, then network address plus 1 will be your first IP address. Okay? And then your last IP address plus 1 is your broadcast address, as long as it's IP version 4. Okay, keep that in mind. So when you're sending data, okay, there are 3 types of routes that it can take. Either it's directly connected, okay. These routes are automatically added by the router, provided the interface is active and has addressing. Okay. Remote, these are routes the router does not have a direct connection, but it keeps updating its table by learning about the network. Now, you can give a manual route, also known as a static route, something you're going to learn in CCNA-2, how to configure a static route. You can also do dynamical route. Dynamical route, you just configure that it automatically learns by itself. This is a better option, dynamical route. Okay. We also have a default route. This forwards all traffic to a specific direction when there is not a match in the routing table. That is how actually your internet works. There is a redundant array of routers connected to each other. How do you think you're surfing the net? How do you think you're downloading your pirated intellectual property? Okay. It's always looking for negotiating and finding a fastest place. Okay. If you are connected to perhaps a series of routers which connects to somewhere in Western Europe, Germany or Sweden, where you're getting your pirated content. Again, which is the fastest route? Is it the router through Thailand, or is it the router through Brunei, or is it the router through perhaps, I don't know, another geographical location? Okay. So that's how actually your routers work. So when I say static route, how you configure it? You configure like this. You say IP route 10.1.1.0. Okay, then I'm saying that if I want to go to 10.1.1.0, I want to go through 209.165.200.226. That means take this route. Here, I'm programming R1. If you want to go to this network, go through 226. Okay, this is your static routing. Okay, Now, unfortunately, sometimes when you give a static route, okay, for example, I say, I configure a static route in R1, and I say that uh, if you want to go, for example, to this network, you have to go through R2. What happens if this network breaks down? You have a problem, right? That means no connection. You may say, then it will go from here. No, it won't. It won't, because you have given a static route. No internet connection. Cannot access Moodle. In those situations, it would be better rather than have, or you can give a static route over here. You can give a static route over here. You know, as a network engineer, you would like to control everything. I will give a static route here, static route there. What if both of them fail? Okay, so it's always good to have redundancy, and it's always better to have, rather than static route, you can have a dynamic route. So the router will immediately, find the shortest path, okay, and connect. So dynamic route is done automatically, finds which is the remote networks, and it will keep on updating that. And it will find the best destination. If I'm using OSPF, open shortest path first, or EIGRP, okay, these are some of the tools that you can use, okay? If the previous path, the best path, is broken, something is wrong, then it will find a new best path, okay? The algorithm for this you're going to learn in your lecture, my dear students, and in your tutorial. In your final exam, okay, you will be asked question about the best path from one hop to another hop. Okay, you'll be studying this in your lecture if you haven't already done so. Okay, it's very interesting. You can actually give the command show IP route. Okay, it will give you in your router, it will give you different codes. For example, L over here means directly connected local interface IP addresses. Okay, C, directly connected network. So L, it tells me this is the one. C, it tells me this is the one. Okay. S is static route was manually configured by an administrator. Is there a static route? Okay. It will tell you even if there is a static route manually configured. Is it on OSPF? It will tell you. Is it on EIGRP? D? It will tell you. Okay. So using the command show IP route, you can find the details of the routes inside your router one. Now, this is only for your knowledge. You're not going to implement it in the lab, not in CCNA-1. CCNA-1 is just mastering the basics, mastering the IP addresses, mastering the connection, and getting your pings right. For your hosts, for your intermediary devices, particularly routers and switch. Maybe I should say first switch and then routers. Okay, remember we haven't touched the router yet in our lab session. We only did switch, 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 which is good. All of you have done well. Okay, all of you have passed thus far. But when you go to CCNA2, now you can actually give a static route if you want. You can give a dynamic route if you want. And you can even check the details of these inside your router. This brings us to the end of today's session. Anyone has any questions to ask? Okay, if you cannot think of any questions now, perhaps later you can think of a question. Very good.